changed it from fluoride to fluorine, but I didn't change this. But it's all right. This is actually false. So if you put down false for this one, then I'll give you two more points. Okay, so take a look at your test, number 25. Okay, other questions? Or maybe I'll just add 2. No, I'll just give you 2. No. You have that too? Actually, here. All right, Ashley and Savannah and Shane. How many people had 25B? Pretty much everybody? Fran, do you have your test? Yeah, yours is different, yeah, all right. Yours is correct. Yeah, it's okay. So basically everybody, just do that. All right, any other questions? I had a question regarding experiment 10. The titration. It was the last part of the lab here. The first part was day 1, and then there's these error analysis here. So try to figure these ones out here, 1 through 6. What you're looking for is an impact on the molarity, the final molarity that you're calculating for sodium hydroxide. And then day 2 here. Day 2, you might do more than 3 runs, but there are 3 places here. If you did more than 3, just add them over here. What we want to do is we want to see the individual runs, because what we want to see is we want to see how well do the individual runs agree with each other. That is, are they all over the place in some kind of random fashion, or are they all clustered around a certain value? If they're all clustered around a certain value, then we say that's pretty good precision. But if they're all over the place, then we say that's pretty poor precision. And so there are different ways we can get a gauge of the precision. One way is to take the smallest value and the largest value and calculate the percent difference. In this case, we're shooting for precision less than 0.5% difference, right? Here. And so you have different choices for the average. For the average, let's say you did 4 runs, and the 4th run, or first run, second run, or whatever, 1 run was an outlier. You could throw that out and just use the 3 good runs for your average here. And so just sum those up. Normally in science, we don't calculate the percent difference between the smallest and the largest runs. What we do is we do a statistical analysis called, what were those, going back to quantum mechanics, what were those boundaries called? For the orbitals, they defined the shape of the orbital and the size of the orbital. They had those boundaries like the sphere, figure 8, the clover leaf. What were those called? Or how were they defined? The boundaries of the orbitals, the shape of the orbitals. Usually people, when they visualize orbitals, they just look at the boundary. Yeah, the 95% probability. And so that's what we do with averages. Normally when we put an average, we want to see, was the spread wide? If the spread was wide, there's a lot of uncertainty. Or was the spread narrow? If the spread's narrow, then it seems to be pretty precise. And we do a little bit of statistical calculations, and normally when we report an average, we get the average plus or minus the 95% confidence interval. The 95% confidence interval gives us a range where we're kind of 95% confident that the true average lies within that range. Those calculations aren't difficult, but we aren't going to do it here. If you have Excel, Excel will calculate it for you if you want. Otherwise, there's a simple equation that we use to calculate. Maybe you're already aware of some confidence intervals, like this standard deviation. Do you know the standard deviation? Have you heard of that? The standard deviation is the 67% confidence interval. So there's 67% chance it's within that standard deviation, plus or minus. But we need to spread it out because we don't want 33% chance of being outside. So we spread it out to 95%, which is close to 2 standard deviations. So we get the average molarity, but the average molarity isn't what's on a bottle of vinegar. What's on a bottle of vinegar is the percent acetic acid by mass. Did anybody already do this calculation? So we have to do this calculation. And if you recall, the percent A by mass is the grams of A over the total grams times 100%. So if we're doing the percent acetic acid, it's going to be the grams of acetic acid over the total grams times 100%. And so we're going to convert this fraction into a percentage. So we need the mass of pure acetic acid over the mass of the acetic acid solution, which is the acetic acid plus water. And so we'll start off with molarity. We're going to have XXX moles of acetic acid per liter of solution. This is pure acetic acid on the top. This is liters of acetic acid solution, which is a mixture of acetic acid, pure, and water. So if we know how many moles of pure acetic acid we have, we can just use the molar mass to get the grams of acetic acid pure. If we know the liters of solution, actually, we don't know the liter. What we're going to have to do is we're going to have to convert it from liters of solution to milliliters. And then from milliliters to grams. But in order to go from milliliters to grams, milliliters of solution to grams of solution, we need the density. The density is missing here, so we're unable to calculate it. If the density is missing, what should we do? So we have 2 choices. One, we could just stop there and say the density is missing, and therefore we cannot calculate it. That's one. It is possible we could try to measure the density, but we're not going to do that. Or 2, we could try to look it up in a table. We're not going to do that either. Or 3, what we're going to do is we're going to guess what the density is approximately. And so what would you rather do? If we guess, that's clearly could be wrong. What would you rather do? Would you rather guess the density or yeah. That comes from this. Read this here, number 4. I'm sorry?
Like that's just the actual one?
Yeah. So think about this for a moment and see, is that reasonable? Is number 4 reasonable thing to do? Oops. And just give me a moment. incorrect, and it's going to lead to an error because we can't assume that vinegar is the same as pure water, right? But the question is, how big will the error be? And it turns out, it's surprising, it's not going to be such a huge error, because if we think about seawater, what do you think of the density of seawater? Is seawater close to pure water? No, seawater is got a lot of salt in there and other stuff, but when we look at the density, the average density of seawater, it's only 1.03 grams per milliliter. So if we assume that seawater was 1.00 grams per milliliter, just like pure water, then we would be off by about 3%. Does that? And so if we make this assumption isn't terrible. And so this is a reasonable assumption. We say, of course it would be better if we had the density. But it's reasonable, but we can expect an error. And so we expect, maybe 1 to 2% error. All right, so would you rather have an answer with 1 to 2% error or no answer at all? Yeah, an answer with 1 to 2%. It's much better than saying, well, we can't calculate it and leave it blank. And so in order to complete this calculation down here, we're going to make an assumption. And that assumption is to assume the density of the solution is 1.00 grams per milliliter. It's likely not. Okay, and then you can complete the calculation. So that's what I wanted to talk about for experiment 10. Any questions on 10? All right, now we're going to start experiment 11. Experiment 11 is going to be a multi-day lab. It's quite involved. And you should skim the lab before, especially these more complicated labs like this. And the first thing is, what is qualitative analysis? And so normally if you go to a UCLA or some place like that, they'll have a pre-lab quiz. And typical question would be, what is qualitative analysis? And you would have to be able to answer that just based on the reading. So you're supposed to read the lab and then figure out what's going on. So can somebody tell me what qualitative analysis is? Or I'll give you a minute to look. Does someone have it? Mm-hmm. Yes. That's basically it. I'll repeat it, but let's think. If I have some deionized water, it should be pure water, right? Because we remove all the contaminants out of it, but are all the contaminants completely removed out of deionized water? And it turns out not. Do you know what's dissolved in pure water here? It's not pure, because you know what we have here? Inside the water we have a little bit of dissolved air. So there's some nitrogen and some oxygen dissolved in the water. Not only that, in air there's another gas. The other gas is CO2. And so there's a little bit of CO2 dissolved in here as well. The CO2 can have an impact on certain properties. of the water. The CO2 is what we consider an acid. It's a Lewis acid. And what happens is, as the CO2 dissolves in the water becomes more acidic. Do you know what neutral pH is? What number they give neutral pH? Yeah, neutral pH is pH 7. And the pH of our DI water is about 4.5. And so it's not, if this were really pure, it would be pH 7. And that pH 4.5 causes this to be quite a bit more acidic, because the difference between, let's say the difference between pH 7 and pH 4 is 3 orders of magnitude, because the pH scale goes by orders of magnitude, like the Richter scale. And so if we have 3 orders of magnitude, that would be 10 times 10 times 10. 10 times 10 times 10 is 1,000 times. And so the difference between pH 7 and pH 4 is 1,000 times more acidic. pH 4 is. This is pH 4.5. Well, anyway, that's dissolved air. But what if our deionizer has malfunctioned? Could you tell? By looking at it, could you tell if our deionizer's malfunctioned? No. And so what we do is we do a simple test. The simple test we do is we run the water through 2 electrodes. And if it's pure, will there be any electrical conductivity between the 2 electrodes? No, because nitrogen doesn't conduct electricity, oxygen doesn't conduct, CO2 doesn't conduct. There's no charge. However, if it's impure, if there's ions in there, will it conduct electricity? Yes. And so what we hook it up to is not a light bulb. We hook it up to a meter. And so you could see, based on the meter reading, if the water's still pure or impure. Well, let's say our deionizer is not working anymore, and the water contains ions now. So the next question would be, what ions are there in water? In other words, what ions are found in tap water? Do you know what ions are found in tap water? Probably sodium, probably chloride. There's probably sodium chloride in tap water. Probably. What else? Yeah, metals from the pipes. If we had lead pipes, we'd expect lead-2 ions to be present. They're trying to, in LA, there's still lead pipes in LA in certain neighborhoods. They're trying to get rid of those. A lot of lead pipes. I guess in Rome, the Romans used lead. Hopefully there's not much lead. Excuse me. But what we want to do is we want to figure out what's inside here. And so what qualitative analysis does is it takes advantage of the chemical properties of lead-2, of other cations, in order to detect their presence. We're not analyzing for sodium, but we can analyze for sodium. That's qualitative analysis. We have another type of analysis called quantitative analysis. In quantitative analysis, not only do we want to detect what's present, we also want to know how much is present. And so in qualitative analysis, what we do is we ID species present. And the results of qualitative analysis is either a positive test or a negative test. A positive test means it is present. A negative test does not mean it's absent. It could. A negative test just means could not detect. Could not detect means it may be absent. Or could not detect means that the test wasn't sensitive enough. That is, it wasn't sensitive enough to detect it due to a relatively high detection limit. Detection limit is how much you need. And different tests will have different detection limits. Some tests are extremely sensitive, like sodium. Sodium's too sensitive. Sodium's so sensitive that we always get false positives because it's so easy to cross-contaminate things. Other tests are too insensitive. That is, you know, you need lots and lots of ions to test positive. So it could very well be there in significant concentration, but we just could not detect it because the detection limit's too high. That is, we need high concentrations to detect. So, so people have thought of a scheme for analyzing ions. So we're going to analyze these 8 ions here. And these 8 ions are 5 cations and 3 anions here. The 5 cations we're going to have is ammonium, silver ion, lead 2 ion, barium, and manganese. And the 3 anions are chloride, sulfate, and nitrate. Some of these ions we test individually. So we'll take this sample and only test for ammonium. And the anions are that way. We only test for chloride, sulfate, and nitrate. So we run separate tests for those. Others of these, we run a sequence of steps. That is separation steps and detection steps. So silver, lead, barium, and manganese are run in a sequence called a qualitative analysis scheme. So in part A, we detect ammonium. In part B, we detect these 4 cations. And then C, D, and E are individual tests for chloride, sulfate, and nitrate, respectively. And so what we're going to do is we're going to go to part B, because part B is the most involved. Part A is just the detection of ammonium. So we take a sample and test it directly for ammonium. So we're going to skip this for now because it's a single test and it's fast. You can do it in minutes and you can do it any time. You just have to save about 3 milliliters of solution to do this test. That's how much we need. So we're going to jump to part B. Part B is a very involved procedure. And we're not just testing for silver. We're testing for silver, lead 2, manganese 2, and barium ions. Probably the best thing is just to take a look at the overall qualitative analysis scheme. So part A is the ammonium test, and then the others are the anion test. We're jumping to part B. This is part B here. All right, in order to carry out this test, we have to have enough sample. So what you're going to do is you're going to measure out 12 milliliters of this. The stockroom is going to give you more than 12 milliliters. You're going to bring a 50 milliliter beaker over the stockroom, and then they're going to dispense more than 12. You need more than 12 because you still need to do the individual tests for ammonium, chloride, bromide, and nitrate. I think. Or chloride, sulfate, and nitrate, I think it was. So measure out using grad cylinder 12 milliliters of cation mixture. We're going to use a large test tube for this. On the one hand, you want as much mixture as possible, because the more mixture you have, the more precipitates and other stuff you'll generate, and the easier it is to detect. However, the disadvantage of having more is the glassware. It's much easier to work with test tubes than beakers. And so if you go too much, then you're going to be switching from test tubes to beakers. Test tubes are a lot faster as far as cleaning goes, and transferring and heating and everything else. So this. Measure out just 12 milliliters. You don't want to use too little, because if you use too little, then you might lose some, and by the end you have nothing left. Okay, then save the rest for the other tests. You know, so this just says save the rest for A, Part C, D, and E. I think that's how it's lettered. And we'll get to those later. So the first step in this procedure is adding HCl. And the second step is to heat it. And so let's look at 1A here first. What happens if we add HCl to this mixture of cations? Well, by adding HCl, we're introducing H plus and Cl minus. Well, the H plus isn't going to react, but the Cl minus could. And so if we take silver ions and react it with chloride, then that's going to form silver chloride. And the H plus will just be alone there, i.e. spectator. And so here we're going to precipitate out silver chloride. But also lead, too, likes chloride. And so if we have lead 2 plus 2 chlorides, that gives us PbCl2 precipitate. And then barium and manganese do not precipitate with a chloride. You know, even if I add 2 chlorides there or more. There's Nr, no reaction. Manganese, the same thing, Nr, no reaction. So this is part A. So in part A, what we're going to do is we're going to generate a precipitate. And this is the precipitate here. It's going to be a mix of lead 2 chloride and silver chloride. The problem with this mixture is both of them look the same. Lead 2 chloride is a white precipitate. Silver chloride is a white precipitate. And so how can you tell the difference? Well, we're not going to tell the difference. What we're going to do is we're going to take advantage of another property of these. This is a physical property. And this physical property is going to take advantage of solubility and temperature. Like, if you think of sugar cubes, dissolving sugar cubes, what do you think? Could you dissolve more sugar cubes in hot water or in cold water? In hot water, right. And so some things are more soluble in hot water than cold water. And you would think most things are more soluble in hot water, but silver chloride isn't so much. So when we use silver chloride and heat it, this triangle means heat, in water, not much dissolves. In fact, just a negligible amount dissolves. However, when we take the lead 2 chloride precipitate and heat it in hot water, it dissolves. But like sugar cubes, you have to kind of crush the precipitate up to get it to dissolve. And so the first thing we need to do is we need to set up a hot water bath. Setting up a hot water bath, it takes some time to get the water hot. I use 2 rings, a gauze, and a beaker. So just find a beaker that fits in the top ring here. This way it doesn't get knocked over. Okay, then I need to adjust the height so that the cone hits the gauze. So I get the maximum amount of heat on the gauze. And then just start heating it. We don't have any boiling chips this time, so just heat it up normally. I just got to make sure that I have enough water here for the test tubes. I don't want it to overflow, but this is enough. You can fill it like halfway or a little more than halfway here. All right, so we're going to have this precipitate. It's going to be a cloudy suspension. And what we're going to do is we're going to start to heat it So now I have both precipitates in here, and we start to heat it. And what I want to do is I want to crush up the lead and the silver precipitate so that the lead dissolves. I need to get all of it to dissolve. It's easy to see when a sugar cube dissolves because there's no sugar cube left. But this is really hard to see because when we eliminate the lead, what's left over? The silver chloride, which looks exactly the same. And so this is very difficult. So what you have to do is you have to carefully see, is the amount of precipitate decreasing? Yes. Is it decreasing? Yes. Is it decreasing? And then eventually it's going to look the same. And when it starts looking the same and it doesn't look like any more is dissolving, and you've been going at it for a little bit of time, then maybe it's all dissolved. But it's a guess whether it's all dissolved or not. All right, there's another complication. And the other complication is people are trying to crush up their lead 2 chloride precipitate like this. And this constant tapping on the bottom of this test tube generates mechanical stress. What are the normal tetrahedral bond angles? 109. But if you keep doing this, do you know what happens to the bonds? It tweaks the angles a little bit. When it tweaks the angles a little bit, the bonds become weaker. And eventually what can happen is this. Let me see if I could do it here. Actually, I did it this morning. It depends on how many people have been doing this. Eventually you're going to go like this and then pop. Do you see what happened? I punched a hole through the bottom of the test tube. And so now all your solution and precipitate will leak out onto the lab bench or inside this. It's happened every semester. It happens. So if somebody punches a hole through the test tube, everything leaks out. They have to clean up and start over. So what I recommend doing is maybe this. To the test tube that you're going to do this, you might want to do a process called annealing. What we do is we heat up the end of the test tube in the hot part of the flame. So I'll heat this up here, and what that does is it softens the structure so that the bond angles can relax back to 109.5. And then I let it cool slowly so that the bonds are in a low stress angle, low stress configuration, and then I let it solidify. And what that does is it makes it mechanically tough. That process is called annealing. So if you're constantly doing this, you're going to generate mechanical stress, and it becomes brittle and easy to break. And so what we'll do is we'll anneal it, soften it, and then let it cool. When we let it cool, this is lab technique and lab safety. We always point the hot end away from you, because normally when you pick it up, you grab the end that's closest to you. And so just grab it. And all right, so again, this is tough. Why is this tough? How do you know when all the lead 2 chlorides dissolve? What's that? Yeah, right. You're not going to dissolve all of it because of the silver chloride. Well, that's fine. All right, so once I'm satisfied that all the lead is dissolved, then I want to filter it quickly. So I need to set up my filter apparatus. The filter apparatus, I use a triangle like this, a funnel. It could be glass or plastic, it doesn't matter. And a ring. And so this would be the filter set up here. Then I need a piece of filter paper. The filter paper is located in a box over there on the counter. And the filter paper comes in round circles like this. And so what we need to do with the filter paper is to fold it in half like this, and then fold it in a quarter like that. And then I'm going to put 3 sheets on one side, 1 sheet on the other. Some people like to tear off a corner, but I've tried it both ways and it doesn't seem to make any difference. And then we'll put it into the funnel, but cause sometimes it pops out of the funnel, so I need to wet it with some DI water here, so that it sticks. Didn't stick very well there, but so that it sticks on the inside of the funnel here. And that should be good. And so then what I'm going to do is, I need to do this quickly. I need to filter this while it's hot. You know, because if it starts to cool down, what will happen? If it starts to cool down, then the lead is going to start to reprecipitate. I don't want the lead to reprecipitate. And so I need to filter this hot so that the lead is dissolved. And what I'm going to do is I'm going to capture it in a clean beaker. I'm going to capture the solution. So this is what's going on here. We're going to separate this mixture into a precipitate and a solution. The solution we call filtrate or supernatant. And so what I want to do is, all I want here is pure silver chloride. And everything else should go over here. So I'm going to filter this hot so the lead makes it there. Okay, and then what I'm going to do is I'm going to wash the precipitate, because the precipitate is going to be coated with the supernatant solution. And so the precipitate's going to be wet with lead, barium, and manganese solution. And so what I'm going to do is I'm going to wash it off by using some hot water here and then just rinsing the precipitate with hot water. The first rinse I do not want to discard. The first rinse I'm going to combine with my supernatant. Here. That's so that I don't lose much lead, barium, and manganese, because there's going to be lead, barium, and manganese on the solution coating the precipitate. So first wash, combine. Second and third wash, discard. Because by the second and third wash, you've washed off most of the supernatant, and so there's very little benefit to adding the second wash. If we add the second wash, yeah, we might get a little bit more of the ion, but the problem we'll have is we'll dilute this. If we overly dilute this, then we're going to be switching from test tubes to beakers, which we don't want to do. Not only that, when you overly dilute it, it makes it harder to detect, because the more concentrated it is, the easier to detect, based on detection limits. So combine the first wash over here, and we're going to wash with hot water. Okay, I washed with hot water. The second and third wash, we can discard into the waste. So have a waste beaker, discard it over there. But the supernatant solution, that is this filtrate solution, is going to be sitting. And as it sits, what's going to happen? The lead is going to start precipitating out again. And so as this thing cools down, you're going to see the lead precipitate. So what I recommend is leave the left branch for later. We're going to work on the right branch here. And so if the lead starts to precipitate out again, then we're going to reheat it to get all the lead to dissolve. So just heat it up. Once all the lead dissolves, then what you're going to do is you can take this solution and add potassium iodide. When we add potassium iodide, lead ions like iodide to form PbI2. PbI2 is a yellow precipitate here. However, the barium, no reaction. Manganese 2, no reaction. So the barium and manganese don't react. We just end up with yellow PbI2. In this one, we only want to do one wash. So we do one wash of this. However, this is a weird sequence because we keep it hot to keep the lead here. But once we precipitate out the yellow, then we want to cool it down. Because PbI2 is also more soluble in hot water than in cold water. So we have an ice bucket over here. And so what we're going to do is we're going to take this and cool this down in ice water. The reason we're going to cool it down is because since this is more soluble in hot water than cold water will precipitate out more. And then we want to make sure we maximize the amount of precipitate. In other words, we don't want any lead escaping here, so we have to precipitate out 100% of the lead. In order to do that, we got to keep an eye on this. Now, the problem is the procedure is written as like a one-size-fits-all. You know, so let's say you go clothes shopping and you go to the one-size-fits-all clothes store. You know, is it going to fit you quite right? What do you think? Or you go buy some shoes. If you want a one-size-fits-all shoes, you go to the one-size-fits-all shoe store and they probably have what size? One size. What size would it be? It'd have to be pretty big. If it's going to fit everybody, maybe like a size, what, 18 shoe or something like that? But is a size 18 shoe, would that be comfortable for you? No. And so what we have to understand is this procedure is written for one size fits all. What's much better is if we can customize the size. You know, so for example, if you wear size 8 or something, you get size 8 shoes. You wear size 13, you get size 13 shoes. But a procedure like this can't do that. You know, because there would be too many. Options. And so what we have to do is this. The written procedure can't do it, but we can do it. And so it might say one size fits all for the amount of Ki. Just add a whole bunch of Ki. But it might be too much, or it might be too little. You know, maybe they got it wrong. Somebody comes by with a size 20 foot, something like that. And so what we're going to do is we're going to optimize the procedure. Optimizing the procedure means how much Ki do you add? You keep adding the Ki until it stops precipitating. How can you tell when it stopped precipitating? How you can tell when it stops precipitating, it's hard to tell. Because you're forming more fog in fog. So let's say it's densely fogged up, or the roads are densely fogged up, and you add more fog. It's hard to tell because it's already so foggy. You can't really tell. Well, it's the same thing here. So what we have to do is we have to let the fog settle. Maybe if the fog settles and you see some blue sky, then it's easy to tell if more fog forms. You know? And so what we do is we let the precipitate settle a little bit and then test it. You know, hopefully the solution clears up near the top, and then we can see if additional fog forms, and additional cloud formation occurs. So something like this, I don't pay attention to how much they recommend I use because that's one size fits all. That's too rough. We can tailor this much more precisely. The same thing here. This is like one size fits all. Add 3 milliliters. Well, maybe that's way too much. Maybe that's way too little. And so the same thing here, but this is very hard to see because that cloudy white takes a long time to settle. However, what helps it settle is by heating it. When you heat it, the tiny crystals come together to make bigger crystals. And the bigger the crystals are, the more they'll settle down to the bottom. And that's a process called coagulation. And so, you know, if it's way too cloudy, heat it up for a bit, let it coagulate, and then maybe the top will clear. And then you can see if additional clouds form as you add more HCl. But what you want to do is you want to do complete precipitation. So we do it here. And complete separations. Complete separations is, you know, we don't want any lead to escape over here. If lead escapes here as a precipitate, then it screws up this next test. We need to make sure that all the lead's over here. And so complete separations are important. And the same thing here. We got to make sure that we have all the lead as yellow precipitate here, because if lead escapes over here, it's going to screw up these results, and we aren't going to get what we expect. And so in this step, you add enough Ki to make sure that there's no more precipitate. Once we do that, then we wash the precipitate once. And we're going to wash it and combine it with the supernatant here because that's going to contain barium and manganese, and we don't want to lose barium and manganese residue coating the lead 2 iodide precipitate. And so the first wash goes here, but I'm not going to do a second and third wash. The reason I'm not going to do a second and third wash is because there are no further steps. If there was further steps, then we want this as pure as possible. But if we stop here, you know, the presence of yellow precipitate confirms the presence of lead in our unknown. And so this is a positive test for lead. Okay, then once we do that, then we're good. We don't have to worry. And then we can go back to the silver. Going back to the silver, we're going to capture the silver chloride precipitate in the filter here. And then what we're going to do is we're going to save the filtrate for the potassium iodide lead test. And then we're going to get a waste beaker here, and then we're going to pour sodium hydroxide in here. When we pour sodium hydroxide on top of silver chloride, we get a metathesis reaction here. And let's show up here. The silver chloride precipitate gets converted into silver hydroxide precipitate. And so this is sacrificing one precipitate, quote unquote, for another precipitate. Which precipitate wins is precipitate versus precipitate. Which precipitate wins is the more stable precipitate in a precipitate versus precipitate competition. Well, something that helps this is the silver hydroxide undergoes further reaction. So if I take two silver hydroxides will form silver oxide plus water. This is a Lewis acid-base reaction, or Bronsted acid-base reaction. This is an acid-base reaction, so we have these. And so what happens is the silver chloride gets converted into silver oxide. And silver oxide is black. And so we're going to convert the white PPT into black PPT by adding sodium hydroxide. If we get this black PPT, then that's a positive test for silver. And we're just going to test it inside the filter paper here. So you're just going to add it here and take a look. Did the color change for the solid PPT? All right, then we're going to go back over here. And again, the dashed lines mean solution, the solid line means precipitate. So now we're working the solution here, over here, barium and manganese. And then what we're going to add is this stuff. What is NaHSO4 called? NaHSO4. Sodium bisulfate. That's correct. So we're going to add sodium bisulfate. And it turns out barium likes sulfate. And so what barium's going to do is it's going to knock the hydrogen off by sulfate. And so barium knocks the hydrogen off and then reacts with the sulfate to precipitate out barium sulfate solid. And the hydrogen is just as H plus residual. Manganese doesn't care. Manganese and bisulfate yields no reaction. And so what we end up with is a precipitated barium sulfate. Again, this precipitate we want to wash. This could be at room temperature. We don't have to worry about cold or hot in this case. Lead salts are especially sensitive to temperature. But here, just room temperature, we wash it with just DI water, and the first rinse will go over here. And we don't need to rinse this further because if we get a white PBT here, that's a positive test for barium, so we don't have to purify this. That's good enough. But we want to make sure we don't lose any manganese, so we'll capture the first rinse over here, and that'll give us the most manganese. The problem is if you lose a little bit here or there, a little bit here, a little bit there, in each step. Let's say the first step you got an 80% yield. The next step you got a 60% yield. The next step you got a 40% yield or something. And then eventually, by the time you get to the end, there's nothing left. So sometimes people get here and they get nothing. You know, their manganese was lost. Where was it lost? It was lost somewhere else. This is a tough step here because the type of precipitate manganese generates. Manganese likes hydroxide, so if I take manganese and sodium hydroxide, manganese wants 2 hydroxides to precipitate out manganese 2 hydroxide. Manganese 2 hydroxide is a light brown precipitate. But the problem is it's gelatinous, meaning it's not a very high density precipitate. It's like a gelatin. And sometimes it's hard to capture and it doesn't seem very dense. And so when you wash it, you know, when we wash this, you start to worry, is it going to wash away all my precipitate? Or will there be some left over? And so what we're going to do is we're going to wash it. However, we don't have to save the filtrate this time because the filtrate is going to be discard. And so we're going to wash this 2, maybe 3 times and dump it to waste. Instead, what we're going to do is we're going to analyze the light brown precipitate. This light brown precipitate we're going to do in 2 steps. The first step is to add nitric acid. I'll call that 6A. And so if we take our manganese 2 hydroxide plus nitric acid, I get manganese 2 nitrate plus water. And so the driving force is going from stronger acid to weaker acid. And essentially what I'm going to do is I'm going to dissolve this precipitate. And so how much nitric acid do you add? You add enough to dissolve all the precipitate. It could be a little, it could be a lot. And then we need a little bit extra nitric acid because this next reaction requires it. And so that's in 6A, dissolve the precipitate. Once the precipitate's dissolved, we're going to add this stuff called sodium bismutate. Now nitric acid is a little bit dangerous because nitric acid is a strong oxidizer. If you get some nitric acid on your fingers, do you know what color it turns? Yellow. And if you have black stains, then you know you touched what? Silver. Silver is also a good oxidizer. And so if you have black and yellow stains, then you have the full complement of colors that we're going to get. Nitric acid is a strong oxidizer, so there's some danger associated with this. Strong oxidizer is what I wrote here. But this one, you don't know the name for this. This is called sodium bismutate. Sodium bismutate is even more dangerous. Sodium bismutate is an even stronger oxidizer than nitric acid. And so you might have had experience with oxidizers in the past. Have you ever inhaled like chlorine, like bleach? Have you ever inhaled bleach? It's pretty corrosive, right? Bleach is a pretty good oxidizer. This is even stronger. And the problem with sodium bismutate is it's a solid. Nitric acid is a solution. And it's a fine powder. It's like powdered sugar. And if you were there with the sodium bismutate and you sneezed, do you know what's going to happen? You're going to get a cloud of sodium bismutate. Just a dust cloud of sodium bismutate. And if you inhale that dust cloud, that's worse than inhaling chlorine. Much worse. And so be careful with the sodium bismutate. If you spill some, clean it up with a wet cloth. If you clean it up with a dry cloth, you might create the dust cloud. A wet cloth should be okay. Not cloth, but paper towel. So this is a health hazard, sodium bismutate, fine powder, powerful oxidizer. What it's going to do is it's going to oxidize our manganese from manganese 2 to manganese 7. Actually, this is manganese 7. And we're going to generate this ion. What's this ion called? Yeah, permanganate. Permanganate looks like purple grape juice, you know, the artificial one. So it has that very distinct color. So what you're looking for is a formation of a purple grape juice looking liquid phase. And if you get that purple grape juice, then that's a positive test for manganese 2. It's a very deep, dark purple color. Except you wouldn't want to drink this one because permanganate itself is a powerful oxidizer. All right, any questions? I'm sorry? Start at part B. For the known, which is day 1, or part 1, we'll have multiple days for this. You can work with partners if you want. For part 2, you have to work individually. Part 2, you're going to be running unknowns. So part 1, when you go through this, if you want, you could work individually or you can work with others. But you have the individual lab for the unknowns. That's going to be mandatory. All right, if there are no questions, I'm going to stop talking here.